Hi, I'm Amir Hossein Mirza Bozorg, and in this tutorial I want to talk about a scratch test simulation in Abaqus Part 1 Paper Validation. How to ask your video related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We try to answer all questions regarding the video details in the comments below. This is the table of content for this tutorial. In this tutorial, the 3D modeling procedure of the scratch test in Abaqus is explained according to a journal article. The scratch test consists of 3 steps. In step 1, the scratching tool named the tip indents the workpiece. The loading is force control. In step 2, the tip travels along the workpiece with a constant speed. Also, the indentation force will continue to increase. The indentation force reaches its maximum value at the end of the second step. In step 3, the tip moves upward, allowing material elastic recovery. The tutorial explains how to simulate all of these, and then it discusses the simulation results. This is the reference paper. According to this paper, the scratch test simulation is performed. This paper investigates the damage pattern, residual stresses, and equivalent plastic strain or PEEQ fields in several different arrangements of multilayer polymetric coatings. This tutorial explains the investigation of one of the arrangements in detail. Now I want to talk about a specimen's geometry. Here we have the specimen and this is the tip. The diameter of the tip is 1 millimeter and the length of the specimen is 20 millimeters. The computational domain was reduced by half due to the width symmetry along the scratch path, which is line AB. This is point A and this is the scratch path and this is point B. The symmetric plane is parallel to the 2-3 plane. This is the symmetric plane. And the specimen must be fixed at its both ends. And this is the FE model from another point of view. The model consists of 4 parts. The first one is the substrate, which is made of PMMA. The second one is base layer, the third one is the top layer, and finally we have the tip. Here we have the studied arrangements of layers in the paper, and I have chosen this arrangement of layers for the simulation. Now I want to talk about the material definition. In this simulation, the tip is assumed to be rigid and all of the materials are isotropic. And here we have the material properties used in the FE modeling. We have the Young's modulus, yield stress, strain hardening slope, and Poisson's ratio for all of the 3 deformable parts. This is the mathematical definition of a strain hardening slope. In the paper, it is assumed that a strain hardening slope is constant. So the plastic behavior will be like this. So we can rewrite the first mathematical definition in this manner. And finally, we have this equation for yield stress. And if we assume that the ultimate plastic strain is equal to 1, so sigma y will be equal to sigma y0 plus h. Here we have the material definition for PMMA. And as you can see, for the second row, sigma y will be equal to sigma y0 plus h. Sigma y0 is 120 according to the table, and h is also 100, so their summation will be equal to 220 megapascal. And also the ultimate plastic strain is assumed to be 1. Now I want to go to Abaqus to show you the model. As you can see, the model consists of 4 parts. This is the base layer, then we have the PMMA, then we have the tip, which is a discrete rigid part, and finally we have the top layer. And I have defined a material for each of the deformable parts. In this simulation, I have assumed that the unit of length is millimeter, and I have used the standard SI units when the unit of length is millimeter. And here we have the assembly. I have used these 2 datum planes to partition the deformable parts. This length is 4 millimeter, and this length, which includes the scratch region, is 12 millimeter, and also this length is 4 millimeter. And here the tip goes downward and travels in this direction and then goes upward. Now I go back to the slides. Now I want to talk about tip horizontal movement definition. Here I have taken these explanations from the reference paper. The FEM simulation of a scratching process was divided into 3 steps. First, indentation, second, scratching, and third, tip removal process. A linearly increasing normal load was applied on the rigid tip following the ASTM standard for scratch testing. To save computational time of the numerical simulation, the tip moves over a length of 12 mm at a constant scratch speed of 4 meters per second was specified. Since rate effect was not considered in the FEM modeling, the relatively higher scratching speed in FEM modeling compared to the experimental work can still be used to explain the scratch behavior. According to these explanations, the time period of the scratching step is equal to the 12 mm divided by 4 meter per second, which is equal to 3 milliseconds. Because of the limitation in the computational resources, in this simulation, the time period of the scratching process is set to 1 milliseconds. Also, the time period of the first and third steps are assumed to be 0.0001 seconds. Now I want to talk about loading definition. Here we have the profile of the normal force. In the first step, it starts from 0 to 1 Newton, and then in the second step it increases from 1 to 10 newtons, and finally in the third step it drops to 0. And here we have the tabular amplitude of force definition. As half of the workpiece is created, so half of the indentation force must be applied to the model. Here I have entered half of the indentation force for the amplitude. And here we have the indentation step, scratching step, and finally unloading step. In all of the 3 steps, the NLGEM is set to on to account for the nonlinear geometry effect. Now I go to Abaqus to show you the related settings. I click on the step manager, and I want to show you the settings of each of the 3 steps. In all of the other tabs, I didn't change anything. Now I want to talk about defining interactions and constraints. I have defined frictional contact definition between the tip and the top layer. Also, I have defined tie constraint between the top and base layer and the base layer and PMMA. I have defined surface-to-surface contact between the tip and the top of the top layer. Now I go to Abaqus to show you the related settings. I go to the interaction module. Here we have the contact definition. And this is the interaction property, which is frictional with the friction coefficient equal to 0.2. This value is mentioned in the reference paper. And I have defined two tie constraints. This one is between the base layer and PMMA, and this one is between the top layer and the base layer. Now I want to talk about mesh definition. Here I have defined two datum planes to use them for creating two partitions. To decrease the number of elements and having an optimum simulation, I have used seed bias to decrease the number of elements and having an efficient simulation. These are the seed bias directions. The size of the elements will decrease along the direction of the arrows. Also here. And here we have the scratch line. I have defined uniform mesh using 512 elements along the scratch edge and its similar edges to maintain the accuracy of the calculations along the scratch line. And here you can see the seed bias directions and the change of the element size. This is the top layer, this is the base layer, and this is the PMMA. I have defined 4 elements along the top layer thickness and 2 elements along the base layer thickness to maintain the accuracy of the calculations along the thickness. Now I want to go to Abaqus to show you these settings. I go to the mesh module. If I remove the tip, here you can see the seed bias. On these edges, I have defined 512 elements, and here I have used single bias, and also here, and also in the other edges, except these edges, which are parallel to the scratch line. Now I go back to the slides. Now I want to talk about the simulation results. Here we have the PEQ contour at the end of the analysis. And here we have the mice stress contour at the end of the first step. As you can see, here we have small deformations because the value of normal force is 1 Newton. And here we have the mice stress contour at the end of the second step. Here you can see the deformation of the elements of the top layer and base layer. Here the value of normal force is 10 newtons. And here we have the PQ contour at the end of the first step. And here you can see the PQ contour at the end of the second step along the scratch edge. The increasing and decreasing pattern of the PQ is because of the force control loading in the Y direction. It leads to the oscillating movement of the tip in the Y direction. Now I go to Abaqus to show you these results. Here you can see the indentation procedure. Now the tip starts traveling. If I remove the tip, and as you can see, the tip is going upward. Here you can see the increasing and decreasing pattern. Here we have the vertical displacement of the tip versus time. This is the first step, this is the second step, and this is the third step. And as you can see, here we have an oscillating movement of the tip in the Y direction. And then these oscillations are removed or damped. By increasing the indentation depth along the scratch line during the second step, the plastic strain of the coating will increase, which leads to the decrease and removal of the oscillations. And here we have the horizontal reaction force to move the tip versus time. This is the first step, this is the second step, and this is the third step. As you can see, here we have large oscillations and then they are going to damp. By increasing the indentation depth along the scratch line during the second step, the plastic strain of the coating will increase, which leads to the decrease of the amplitude of these oscillations. Now I go to Abaqus to plot these curves. RF3, and also U2. Here, I want to compare the PEQ contour of three parts at the end of the analysis. This is the base layer, this is the top layer, and this is the PMMA. As you can see, for all of the three deformable parts, the PEQ is greater than 0. It means that in all of the three parts, we have plastic regions. But in the top layer, the maximum value of PQ is more than the maximum value of PQ in the other deformable parts. Now I want to compare the obtained results with the paper results. In the paper, in figure 9, part C, we have the plastic strain and stress contours of the T30B15 specimen. And I want to compare this picture with the simulation results. I use view cut. And here you can see that the range of the values are similar to these values. Also, their color is similar. Now I go back to the slides. The package, including Abaqus files, is ready to purchase. The package price and payment details are provided in the video description. Now I want to talk about next tutorial content. The following tutorial will explain a simulation of the scratching test, including cohesive interaction between the coating layers and illustrating the delamination pattern. Actually, in the next tutorial, we will define cohesive interaction between layers instead of tie constraint to calculate the delamination. And here, as you can see, we have the delamination. This is the contour of damage initiation parameter for cohesive interaction. And here we have the damage propagation parameter for the cohesive interaction. As you can see, we have complete delamination between the base layer and the PMMA. But the cohesive interaction between the top layer and the base layer is not totally damaged. And even here, we can see the delamination visually. You can contact me using Telegram or WhatsApp, or you can send email to me. We can have one-on-one tutoring on the AnyDesk WhatsApp, and we can make special tutorials to your order. We can conduct high-quality simulations for your thesis, exercises, and industrial project. And we offer support in writing the modeling and result discussion part of your thesis. Also, we have consulting services for MSc or PhD positions or job interviews, and we can help you to prepare the presentation of your simulation works. Now I want to suggest you several related videos of our YouTube channel. Thank you so much. Have a good time. Goodbye.